So let's talk about how pressure and temperature can affect the solubility of solutes in different solvents. We're going to talk about gases, and we're also going to talk about some solids and how they will be affected when we're trying to dissolve them into different solvents. Again, what you are dissolving is your solute. What you're dissolving it into is your solvent. If your species changes phase, meaning like a gas dissolved into a liquid, the species that changes phase, so that gas going into the liquid phase, is your solute, or your solid going to a liquid phase is your solute. If you've got two things that are in the exact same phase and they're mixing, so two solids mixing or two liquids mixing, your solute is what's present in the smaller amount. Again, when it changes phase, it's whatever changes phase that's a solute that may be present in a greater amount. So when they change phase, it depends on what changes phase. When they're in the same phase, your solute is what is present in a smaller amount, just to make sure everyone's on the same page. So, some properties of solutions. The effect of temperature on your solubility. What we have found experimentally is that the solubility of a solid into a liquid usually, not always, but usually increases as I increase the temperature. And if I look at the graph here, that's what I see happening. I've got on the x-axis, I've got my temperature. So you can see here we're increasing our temperature going from 0 to 100 degrees C. On the y-axis, we've got your solubility, and that shows grams of solute in 100 grams of water. So that's showing you how many grams of the solute can I dissolve into 100 grams of water at these varying temperature ranges, okay? And I see for most cases, an exception here being the cerium sulfate compound, most cases, the solubility is increasing as I increase that temperature. That shouldn't really surprise us though. As I increase the temperature, I'm giving those molecules more energy to move around, but also more energies to break apart that solute-solute interaction and the solvent-solvent interaction, which will better allow the solute-solvent interactions to form. So again, I'm putting energy in. I can break apart the solute-solute, the delta H of solute-solute, the delta H of solvent-solvent. Because remember, this is your cost. And these have to be broken apart, or these have to be overcome. So the amount of energy required here, this is your cost, or your payment, whatever. This is how much you're paying to the system. This is what I have to add in. This is your endothermic process. So I'm putting more energy in, allowing the more temperature puts more energy and allows those things to break apart. And I see every compound here, with the exception of, again, the cerium 3 sulfate, is increasing the solubility. Even sodium chloride, it's not a huge increase, but I do see starting down here at around 30, just maybe 34 grams per 100 grams of water, up to 40 by the time I go up to 100 degrees C from 0 degrees Celsius. Now, what I also find though, experimentally they've determined or found that the solubility of gases in the liquids actually decreases as I increase the temperature. That also shouldn't surprise you though. Gases bubble through the liquid and they form IMFs, form those attractive forces with the other molecules in solution, holding them into solution. But they were a gas to start. And so the gases, if I give the molecule more energy, they have the energy to completely escape the solution and go into the gas phase. So again, solids will increase solubility with increasing temperature most of the time. But gases, we see a decrease of solubility as I increase that temperature. So one important application of this is thermal pollution of lakes and streams. Just to show you why does this matter? And it's this idea here. Sorry, I'm trying to hit the right button on my iPad and it's not working. Power plants are often located next to rivers or lakes. That's kind of a common knowledge thing. Most people don't really think about it. Most people know, like, oh yeah, that makes sense. It's located next to a river or lake. And this is because they use the water for two purposes. They use the water to not only harness power to run the power plant, or to pull the power off of so they can, power our electricity source and our electric grids. But also that water source cools down these large systems that are running because they do generate heat. And we need to cool them down so that they don't, overheat, explode, blow up, etc. But when the waters return to the lake, the water returning to the lake will most often be at a higher temperature than it was when it before it was pulled into the power plant. Because as a heat sink, as a way of holding down that heat in the solution, when it runs through that system, the heat travels from the system into the water. right? Transfer, remember thermochemistry, the transfer heat is neither lost nor gained, it just transfers. So it's transferred to the water. The water being returned to the lake is at a higher temp, which means that the oxygen in that water is less soluble. The oxygen gas that's been bubbled in, that's naturally in water, is less soluble in that water. So there's less oxygen dissolved into the water. Fish survive by relying on that dissolved oxygen for respiration. There's less oxygen in the water, it leads to more fish death. That's why you'll also see that, bottom line, there's less fish living near the power plant than there would be in an area, say, that's not affected by that. So just kind of an application of it. Thermal pollution is that heat being added to the water from those power plants. How can I apply this though? What does this graph mean and how can I look at it? So it is slightly cut off. Remember on the up here we see it does go up to 100. Down here we see it's slightly lower. Just the way I have the slide formatted, cut it off just a little bit, but it does go up to 100 degrees Celsius. Again, the grams of solute in 100 grams of water. So the first question we have here is how many grams of sodium chloride are required to saturate 500 grams of water at 100 degrees C? First thing is remembering what saturate means. Saturate is how much can I dissolve based on the solubility of that solute in that solvent at that temperature. It's the maximum amount that will dissolve. So if I want to look at 100 degrees Celsius, of course sodium chloride is cut off at 100 degrees. So I'm going to slide back up to the previous slide just so we can look at this really quickly. Okay? So if I look here, I both love and hate this feature of scribbling. If I look here at sodium chloride, 100 degrees, I can see that this is clearly requiring 40 grams of solute and 100 grams of water, okay? So sodium chloride, I'm going to scroll back down here. I want sodium chloride, and I found that it required 40 grams. Whoops. I'm hitting all kinds of things with my iPad. I apologize. It was 40 grams of NaCl per 100 grams of water. But notice here I want 500 grams. So what do I need to do? I need to multiply that number by 5. I want it for a value of 500 grams, not just 100. So to saturate 500 grams of water at 100 degrees C, I would need 200 grams of NaCl. Again, multiplying this number by 5, multiplying this number by 5. Second question, if 30 grams of KCl is dissolved in 100 grams of water at 45 degrees C, how many additional grams of KCl would be needed to make a saturated solution at 80 degrees C? Well, here's the tricky part. That 30 grams of KCl in 100 grams of water at 45 degrees C is only slightly important. It's important that I understand I already have 30 grams in solution, but that 45 degrees Celsius, useless information. What I'm really asking here is how many grams of KCl are required to saturate the solution at 80 degrees C. So that's where I need to focus my energies. So if I look at 80 degrees C, go up, and I see it's right here. Take that over, and it's just above 50. So say 51, 52, somewhere in there. Let's just say 52 grams. 52 grams are needed in 100 grams. But I already have 30 grams present, which means I just need the difference. I need about 20 to 22 grams, and I would accept any of those answers on this. 20 to 22 grams of KCl additional to saturate that solution, because I already have 30 in there. So again, the 30 grams of KCl dissolved in 100 grams of water at 45 degrees C is important in the sense that I know I already have 30 grams present. The 45 degrees C is just useless information. It's just there to throw you off. Why do we do that? Because the real world gives you information all the time to throw you off. And whenever you go on, whether you go to, graduate school or dental school or farm school or medical school, whatever it may be, you are going to be given useless information and you're going to have to disseminate it. So we do that here as well. If 50 grams of water saturated with potassium chloride at 23 degrees Celsius is slowly evaporated to dryness, how many grams of the dry salt will be required? Let's talk about what that means. What this means is I've got a beaker here, okay? And we're going to pretend that was not that crookedly drawn. Okay, I've got a beaker here that I have, what did I say? I have 50 I have 50 grams of water. And I have currently an unknown amount of KClO3 in it. I will tell you, we'll figure out how much we have in it in just a sec. I have this much present, okay? And I know it's saturated, which means that I have the maximum amount of KClO3 that I can have based on this temperature and this amount of water. If I look up KClO3 on the table, where is my potassium chlorate? There it is. Here's my potassium chlorate, okay? I look at 23 degrees C. I'm going to say 23 is right here. It's close, somewhere around here. I run my line up and I see where I intersect. And I run over. I'm going to say that that is about 8 grams of KClO3. But remember, that is in 100 grams of water. So I have 8 grams of KClO3 per 100 grams of water. But I only want 50 grams of water because I said I only have 50 grams of water with this amount in it. So I'm going to divide this all by 2. That means I would have 4 grams of KClO3 in 50 grams of water. So I got 4 grams of KClO3 in here. Now it says the solution is slowly evaporated to dryness. What that means is all of the water has escaped. All that's left behind is the salt. I know that I have 50 grams of water. I know 50 grams of water can contain 4 grams of KClO3. So therefore, once all of the water is gone, I will have 4 grams of the KClO3. Okay, question 4. A solution contains 36 grams of sodium chloride in 100 grams of water at 90 degrees C. Is it saturated? If I look really, really close here at the 90 degrees C, I can see it's just below the 40 mark for NaCl. It requires 40 grams, and I know from the first example it requires 40 grams of NaCl to saturate 100 grams of water. But again, this is asking at 90, and it's saying I have 36 grams of NaCl present. If I look there, the 36 is going to be, roughly here, maybe a little bit lower than this. I can draw a straight line with the iPad's help. Probably slightly lower than that. Truthfully, I probably drew that too high. Probably right here. I see that it's definitely, the saturation line is definitely lower than the NaCl line. So yes, this solution is absolutely saturated. 36 grams of NaCl in 100 grams of water at 90 degrees C, yes, it is saturated. Now at 100 degrees C, it would not be saturated. I would need to add a little bit more. I need to add about 4 more grams. But at 90 degrees, the solution is saturated. Let's talk a little bit more about the effect of pressure, or solubility with the effect of pressure. Now, this is going to be affecting your gases, okay? So temperature affects your solids and your gases with their solubility, but pressure is really going to only affect your gases. The solubility of solids in liquids is not greatly affected by the pressure overall. It really doesn't really have a big effect on pressure. But gases are absolutely affected by the pressure. The solubility of gases is directly proportional to the partial pressure of that gas over the liquid. So remember, partial pressure of the gas is how much of that total system of gas molecules, or the total pressure of the system is due to the gas that we're looking at. And the partial pressure is how much is due, again, specifically to that individual component. Because the pressure is made up of all the gases that are present. Over the liquid means that above that liquid. What is the partial pressure of the gas above that liquid? That is directly proportional to how soluble it is in the solubility of that gas in that liquid. We have Henry's law, so we have an equation here that we can use to actually calculate it. And we can see here, Henry's law states that the solubility of the gas in a liquid is equal to Henry's law constant, which would be given to you, or you would solve for it given the other 2 pieces of information. It's a simple algebraic equation. So Henry's law constant for gas or liquid mixture, and then the partial pressure of that individual gas. So you can actually calculate the solubility here. What I want you to think about, though, is that if I increase the pressure, the solubility of that gas increases. And that's what I see in the pictures here. If I look at this first picture here, A and B, okay? The little purplish blue dots are the gas molecules. And we can see here, where we have a lower pressure, we have more of them in the gas phase. As I increase the pressure, remember, increasing pressure decreases volume. and I see that more of them go into the liquid phase below. Same thing when you guys open up a can of any type of pop. We see when you open up, remember when you open up that can, you hear that, right? Sometimes you can see it, sometimes you can feel it, but you see the CO2 release. Well, that's because when you've got the can, you've got CO2 dissolved in that solution. That's what's making all the bubbles, is the CO2. So the can's under pressure. I open it up, that pressure is released. Now the system is under less pressure, and the CO2 bubbles will release and bubble out of solution as well. It's also why you don't shake the can before you open it, because otherwise it will release it a lot faster in your face. You can see here as well, if I'm under equilibrium versus when I change the pressure. Equilibrium, again, just means I have a steady state of the molecules. It means that for every one molecule here that goes in, one molecule here escapes, okay? But if I increase the pressure here, I see that the more molecules have gone into solution. If I increase the pressure, if I increase the pressure, more particles go into solution, and then as the equilibrium is restored, the system does reset itself. So two important applications here are the bends in a hyperbaric chamber. So the bends is, most people have heard about this, but if you haven't, it's due to deep sea diving. When you go really far deep into the ocean, like really deep into the ocean, it's called deep sea diving. Well, the pressure on your body is different than what we have here where you're normally living at, well, depending on where you live. Here in North Texas, we're pretty close to standard pressure, a standard pressure of 1 atmosphere. But the bend is also known as decompression sickness. When a diver surfaces too quickly after being down at those heavy depths, the gases that were dissolved in the bloodstream become less soluble because the pressure isn't as great. So as the diver goes under, the gases that are present dissolve into their bloodstream easier. Now they're rising to the top, and if they rise too fast, the pressure isn't there anymore. The gases are bubbling out of their bloodstream. The gases become less soluble and they bubble out. But the bubbles themselves tend to collect in the joints of the diver because they need to collect somewhere. So the bubbles tend to collect in joints, and it can cause great pain to the diver, and unfortunately can even lead to death if not done carefully. That's why when someone's deep sea diving, they have to be brought up at a certain rate so that the gases can slowly dissipate from their bloodstream in a safe manner. A treatment for this would be the hyperbaric chamber. This is where the person is put into a chamber with 100% O2, just running straight through. And it's the high pressure of that gas that allows the oxygen gas, that allows those other gas bubbles to dissolve and the person to survive. I hope this helps understand solubility a little bit. Again, temperature has a solubility effect on both both solids and gases. The increase in temperature up here, increasing temperature causes solids to be more soluble in the liquids because I'm putting energy in, I'm breaking apart those solute-solvent and solvent interactions, I'm allowing the solute-solvent interaction to form. So even if it wasn't favorable, it most likely is more favorable now, but again, there are exceptions to that rule we see here with this, like cerium-3 sulfate. Liquids in liquids, that's, kind of same idea. Gases in liquids are less soluble as I increase that temperature because the gases now have more energy to completely escape the solution. When it comes to pressure doesn't really have a big effect on the solids going into liquids, but pressure has a large effect on the gases going to liquids. Greater pressure causes those gases to dissolve easier into liquid. Less pressure, the gases escape more easily.